So a photon checks into a hotel and is asked, "Do you need help with your bags?" And the photon replies, "No, I'm traveling light." Because a photon is a packet of light, and it literally is traveling light. What are you going to do? What are you going to do? Hey, today we're talking about the 13th topic of 13th topic, which is equilibrium. We're going to do lesson 2, which is LeChatelier's principle. So let's talk about this principle, LeChatelier's principle. And this states that if something is changed in a system at equilibrium, the system will respond to relieve the stress. For instance, there are 3 different things that I'm going to talk about on ways you can stress a system. The first being changing the concentration of either the products or the reactants. But if we change the concentrations of a system at equilibrium, that will stress a system. Another thing we can do to stress a system is change the temperature at which the system is at. And finally, changing the pressure. But this only is important when we talk about gases, so if we change the pressure of gases. So let's get into some of these examples. So if we change the concentration by adding reactants or increasing the concentration of the reactants, some things are going to happen. The forward reaction will speed up. So the reactants will start turning into products as more products form. And the equilibrium is said to shift to the right when this happens, because the reactants are going to form products. So if you have a system at equilibrium and we add more reactants, the reactants will be able to react with each other more, and it will speed up the forward process. This means more product will form, and the equilibrium shifts to the right. I used an analogy before about like a shopping center, a 2-level shopping center. So for instance, let's say the reactants are the first floor and the products are the second floor. If we add more reactants, that means more people come in on the first floor. Some of these people are going to inevitably be interested in what's on the second floor. Not all of them, but some of them. So what happens when you add more reactants or add more people to the first floor, you'll find that that it'll speed up as more people are going to start going to the second floor. And more people will start being formed. There'll be more people on the second floor, which is more product, if we said the bottom floor is reactant and product. This is a great video I have for you guys. So I'm going to show you a video about this, and they use tanks of water, which I really like, to explain this perhaps better than a shopping mall. So take a look at this.
When we add water to the tank on the left, the water in the tank on the right moves up, and that on the left moves down. The water moves from left to right, so we say that equilibrium shifts to the right, as it would if we added more reactants to a reversible chemical system.
Now, this is a great video for a few reasons, as far as I'm concerned. So, if you notice here, this is a good example of something at equilibrium, and the water levels are at equilibrium. It might not be chemical equilibrium, but it works. It's a very, very good analogy to use. So, if you take a look here at this situation here, if we have equal amounts, or the equilibrium is the same, but you notice that the tanks are not the same. The volume of the tanks are not the same. In other words, if this left side here would be our reactants and the right side would be our products, you notice that it's not the same amount of reactant and products. So I really like that they didn't make the tanks the same size. And you also notice that the water molecules are free to move around from tank to tank. But if water molecules move this way, other molecules are going to move back the other way. So you have this equilibrium, that the level of the tanks are not changing. Now, as we go through this here, if we add water to the left tank, which is the reactants, then what's going to happen is that water is going to be forced through the pipe here and increase the level of the other side here. So the water will move over to this direction here, and so as it shifts, let's see here. As it shifts from the left to the right, we're getting more product. So again, to reiterate what we talked about on this last slide here, if we add reactants, that would be like adding water to the left tank, the forward reaction will speed up, so water moves to the other direction. More product will form, and the equilibrium shifts from reactants to products. Now, we can also change concentrations in another way. What if we add more products instead of more reactants? Well, let's think about that in the terms of the tank. If we add more products, then the reverse reaction speeds up because the right tank is going to be filled and it's going to move to the left tank. More reactants will form because as you add products, the reverse reaction speeds up, making more reactants. And we say that this is an equilibrium shift to the left as the products become the reactants. So if we take a look at this with the water example again.
Adding water to the right tank causes the water of the left tank to rise as water moves from the right tank to the left. Equilibrium in the system shifts to the left, as it would if we added product to a reversible reaction.
Great. So there's another thing we can do here is, what if we remove products? So you can change concentration by adding reactant or adding product, but we can also remove things from an equilibrium system. So if we remove products or decrease the concentration of the products, the forward reaction will speed up. The forward reaction will speed up to compensate for the loss of the products. This means more products will form, and the equilibrium is shifting to the right. The reactants are going to be forming products. So these are the things that are going to happen if you remove products. And if you think about tanks of water, maybe, if you take a cup and remove some water from one of the tanks and the products would be the right tank, these are the things that would happen with that. So let's take a look at that.
Removing water from the right tank lowers the water level of the left tank as water moves from left to right to regain an equilibrium. The equilibrium shifts to the right, as it would in a reversible chemical reaction if we subtracted product from the system.
Okay. And the last example, since we've added reactant and product, and now we remove product, how about if we remove reactant? You should be able to mentally go through all these different steps in questions about equilibrium. So if you remove reactants, the reverse reaction will speed up. So remove reactants, we're removing from the left tank. And so the reverse reaction speeds up because the products, the right tank, will be filling up the left tank. So the reverse reaction speeds up, more reactant will form to compensate for that loss in reactants, and the equilibrium shifts to the left because products are going to form reactants here.
Removing water from the left tank causes water to move from the right tank to the left. Equilibrium shifts to the left, as it does in a reversible chemical system when we reduce the quantity of the reactants.
So, I love this analogy with tanks and water, and in fact, I use this a lot when I'm dealing with stressors to systems, LeChatelier's principles. I will often think about the tanks of water. So if I add this, it's going to move this way. If I remove, it's going to move that way. If I just think of that, I really don't have much problem answering LeChatelier stressor type questions. And that's why I'm showing you this, because I think these are excellent videos, good analogy for this. And just remember, when we talked about the first lesson here, we talked about a K value, an equilibrium constant. And if we think about this mathematically, if you were to remember, let's pretend K is 1, just to make it simple. So K is 1, it could be 1 over 1, because remember it's products over reactants. It could be 2 over 2, 3 over 3. There's an infinite amount of possibilities, but K is always going to be equal to 1. So if you remove something from one side, then it's going to have to compensate. The other side is going to have to subtract some from the other side to kind of fill that other side up until both sides are equal again. So there is a mathematical process behind this, and it does get a bit complicated, but you can do it. I know you can. Now, another thing we can do to stress out a system is change the temperature. So we can change the temperature of a system, and that will it'll stress the system in equilibrium, because all reactions either require or release heat. reactions are either exothermic or endothermic. In endothermic reactions go faster at higher temperatures. Endothermic reactions go faster at higher temperatures. So let's think of an endothermic reaction. Endothermic reactions are when the system gains energy. So an endothermic process could be like ice gaining energy to become water. That's an endothermic process. The ice is gaining energy as it's becoming water. Does ice turn into water faster at higher temperatures? Yes. So think about examples that you understand and think about it. Try to practice it often so that when you do chemistry test questions, you're comfortable with putting that together and getting the correct answer. Exothermic reactions go faster at lower temperatures. So an example of an exothermic reaction would be water becoming ice. Exothermic. Exothermic means heat is leaving the system. For water to become ice, energy has to leave the water to become ice. Energy has to go to the surroundings. So that's an exothermic process. The water is losing heat energy to the surroundings. And water becomes ice faster at lower temperatures. That's true. The lower it is, the faster the water will become ice. All reversible reactions will be exothermic one direction and endothermic the other direction, because all reactions are either releasing heat or absorbing heat. So if it's absorbing one direction, it's releasing the other direction. Therefore, reactions that have a change in temperature will always, equilibrium, reversible reactions, dynamic equilibrium, when you change the temperature, will affect the shift one way or another because temperature is part of this process here. So let's take a look at something here.
In a sealed flask, we have a mixture of dinitrogen tetroxide, a colorless gas, with the brown gas, nitrogen dioxide. When we heat the flask, however, the dinitrogen tetroxide decomposes into nitrogen dioxide, creating more of the brown gas until equilibrium is reached for the higher temperature.
So let's talk about this more in terms of shifting things. If we take a look at a reaction, let's just do a real simple reaction here. We'll say A plus B is in dynamic equilibrium with C plus D plus energy. Because I wrote energy as a product, this would be an example of an exothermic reaction. This is exothermic because energy is a product. It's releasing energy in this. So if we were to change the temperature, if I was to increase the temperature, think of it this way, if I increase the temperature, and we understand LeChatelier's principles of concentrations, if I increase the temperature, that's like adding more energy. And you can think of energy as a product. So if I was to increase the temperature, it would have a shift to the left to deal with that. An exothermic reaction would shift to the left if you increase the temperature. If I decrease the temperature, it'll shift to the right because I'm losing product. So if you think about these as the two tanks of water, it's kind of easy to just think of energy and temperature. Temperature is adding or increasing. Let's do another one. We'll do E plus F is in dynamic equilibrium with G plus H. But this is going to be an endothermic one. I'm going to say energy's on this side. Endothermic. So in this endothermic reaction, if I was to increase the temperature, then think of adding more energy, and energy is a reactant. So if I increase the temperature on an endothermic reaction, so it would shift to the right, or the forward reaction would speed up and more product would form. So if you think of energy as parts of the equation when you do endothermic and exothermic, if you're comfortable with doing this, then and you're comfortable with LeChatelier's concepts of changing concentrations, it works right there, right directly with it, and it helps me a lot to figure out questions like that. That's how I my brain works it out. It's, hopefully it helps. That's all I'm trying to do. Just trying to help. All right. The other thing that we can talk about in changing is pressure. If we change the pressure, that a system can adjust to these changes in pressures accordingly to deal with the new changes in pressure. So if you increase the pressure, the system, remember these we're talking about gases, will adjust to create less gas molecules or less moles of gas in the process. So in this example here, at a high pressure, hydrogen and oxygen would become water, because you've got 3 moles of gas to start with. You got 2 moles of hydrogen and 1 mole of oxygen becoming 2 moles of water. So 3 moles of gas becoming 2 moles of gas. At high pressure, this would be ideal because you have less moles of gas. So it's going to reduce the, to basically, because it's more confined, it will switch to a system that has less moles bouncing around, so it's not as crowded, if you want to think of it that way. Now, what if we have low pressure? If we have low pressure, the reverse is true, because we have 2 moles of gas, we'll make 3 moles of gas. And this is entropy driven, more disorder. If you're allowing more freedom, the law of disorder says that things are going to go towards disorder. So if you allow more freedom because you have lower pressure, the 2 moles of gas will shift to make 3 moles of gas. Now this is an interesting concept that a lot of people get confused about. Adding an inert gas does not affect the equilibrium. Well, adding an inert gas increases the pressure. We can increase the pressure of something by adding an inert gas. By the way, an inert gas is something that doesn't react. It's not part of the system. It's not going to react with the system. So how does this not affect the equilibrium? Well, adding an inert gas, if you take a look at this picture over here, let's see. If we take a look at this picture over here, if I add an inert gas, that would be basically a gas that's not like these guys here. So you see these nitrogen dioxides combining together to make this dinitrogen tetroxide. If I have an inert gas, it's not going to increase the collisions. If I decrease the volume here, it will increase the collisions because there's less space between them and they'll collide more often. Remember the collision theory. But if I add an inert gas, the collision with the inert gas doesn't make the reaction happen. It would just bounce off other things and it wouldn't actually make this reaction go faster. Let's look at this illustrated. It might help doing that right now.
A sealed flask contains 3 molecules of nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
So to compensate, I like the way that was worded, to compensate for the decrease in volume, it shifts to have less moles of gas in the system. And it would also be true if we expand the volume to allow it to shift that way. And again, an inert gas doesn't make it more likely to collide into each other faster, more often, faster, or in a better orientation. So it's not going to change the reaction. It's not going to speed up any one of the directions when you have an inert gas because it's not part of the reaction.
A sealed flask contains...
Okay, so I got 5 questions for you on this one here. Can you tell me with this equilibrium expression here, this reversible reaction, how the reaction would be affected if you do one of these 5 things? So pause the video right now and try to answer these 5 questions. Give it a try. Pause. All right, hopefully you did. Don't cheat. Let's see how you did. So if we add hydrogen gas to this, what would happen, and explain why? If we add hydrogen gas to this, this equilibrium's process, there's going to be more likelihood that because there's more hydrogen, that it will collide with nitrogen, and therefore it'll make more ammonia. So adding hydrogen gas to this reversible reaction will cause a shift to the right, and more product will form. So the forward reaction will speed up, it'll shift to the right, and more product forms. How about if we remove nitrogen? If we remove nitrogen, then what will happen to compensate for that is the ammonia will break apart into more hydrogen and nitrogen to compensate for the removal of the nitrogen. So if we remove reactant, the product will be used up to replace the reactant. So the reverse reaction will speed up as more reactants will form in that process. In the third one, what if we remove the ammonia? Well, if we remove the ammonia, then more nitrogen and hydrogen will react to replace that ammonia. The reactants will react to replace the product. The forward reaction will speed up as more reactants form products. Number 4 is a little more tricky, and I hope you tried it before I tell you the answer here. Increasing the volume, because you do get a lot more out of things if you try yourself than you just do if you're just hearing answers. So increasing the volume, how does that affect the equilibrium here? Well, if you increase the volume, you're decreasing the pressure. And if you decrease the pressure, that allows more freedom for a gas. The gas is going to move towards higher entropy, more disorder. So you're going to have more disorder going from 2 moles of ammonia to, or 2 moles of product, gaseous product, to 4 moles of gaseous product. So it's going to shift to the left as products form reactants. It's going to be a left shift if you increase the volume. Why? Because if you increase the volume, you're decreasing the pressure, which is going to move towards more entropy as far as gases are concerned, and you have a 2 to 4 ratio, so the 2 is going to become 4. Finally, what if we add helium to this system? Well, helium is a noble gas. It's not part of this equilibrium system. So this is an example of an inert gas. This is not reacting with this. So if we add an inert gas to this, yes, it does increase the pressure, but it will not change the equilibrium here, because although these will be bumping together, there's more pressure, but it'll be more collisions because some of those collisions are with the helium, and that does not make more collisions with each other adding the helium. Therefore, there is no change to the equilibrium when you add the helium. I hope that makes sense, and I will talk to you guys soon. Save those questions for me. Bye.